Okay, looks like we have some people coming in. That's excellent. While people are coming in, I am going to put up just a quick survey to our screen. Let's see here. Okay. So what we have here is I'm just trying to get a feel for who all is in the room and kind of tune my presentation accordingly. So we'll just take a minute or so, take a look at these answers here. So there's two questions here. One of them is, what is your level of experience with graphs? And, I don't like to assume anything at a conference like this. There could be a lot of students here who are just learning, and that's fabulous. So just want to give everybody a chance. Okay. All right. I'm going to end this poll in about 10 seconds. So speak now or forever hold your peace. Okay, in 3, 2, 1. Okay, we're going to end our poll now. So thank you for those who responded. I just want to introduce myself. My name is Clair Sullivan, and I am a data science advocate at Neo4j. And if you're here, it's because we're going to be talking today about making knowledge graphs in using some machine learning tools. So I am going to dive right in. This is going to be a live coded workshop. You don't have to code along. It's totally fine. I just wanted to give that option for anybody who wants to, or you can just watch. It's all good, whatever you like. So I'm going to start by sharing my screen. Okay, and I'm going to go. Okay, so Elias, if I'm not sharing, let me know, but otherwise I'm just going to get started. So, like I said, my name is Clair Sullivan.
Great.
Okay, cool. Yay. Just here's a couple ways that you can reach me online. I do a lot of blogging on Medium, which is that first link there. And then the other way to get a hold of me is on Twitter, particularly if you have questions about today's workshop. I'm going to do my best to try and be watching the chat window, but just the way the interface works, while I'm doing a full screen share like this, I can't always see what's happening in chat. So if you have questions, feel free to hit me up afterwards, and I'll try to get to them as soon as I can. And let's just dive into the content. Today we're going to be going kind of fast, but I will have a GitHub repository with all this code that I'll share with you. And so you can always like write issues on that repository if you want to have some more long-term discussion than you can do in the normal Twitter character count. So, okay. Now, most of the people here probably already know what a knowledge graph is. I'm going to do for the students in the room and those who are new to this subject, I'm going to do a quick overview of it. But yeah, so what if I told you all knowledge is controlled by Google? Okay, I will put this link up several times today. This is all of the materials for today's workshop. And one of the things that's not in there is that I actually have some questions to ask you guys, some coding questions. We're going to be using a query language called Cypher today. And so there'll be, if you give me like a day or so, I'll put the answers, the solutions up into the repo. Okay, so if you want to live code today, we're going to be using a few different things. First, we're going to be using either Jupyter or Colab. Colab you can run just from your browser if you're not familiar with it. Jupyter, in the repository, there are some dependencies that you're going to want to install. So just, you can go either way, but check out the repo if you're wanting to to do this on your own machine. The second thing that we're going to be using are Neo4j sandbox instances. So Neo4j, for those who are not familiar, graph database, and basically these are pre-configured databases. They're free. You can get blank ones. You can get ones that are already pre-populated. We're going to work with a couple different knowledge graphs today that we'll be doing within Sandbox. Okay, so moving right along. Those of us who do data science and machine learning in this room as part of our profession, we know that there's a whole bunch that goes into it, and the general idea is garbage in, garbage out. So if you put garbage data into your model, you will get garbage results out. And we can play little games. We can stir that pile like our XKCD comic says here. We can try to make our data more appropriate to our model, but the problem is that if you don't have good data, as we're going to see today, you're not going to get good answers out. Okay, by the end of this workshop, you're going to be able to apply data science and machine learning to knowledge graphs. I'm going to kind of work backwards in our sequence here. But what does that actually mean? How are we going to do that? Well, machine learning, as you know, is based on taking whatever our data is and turning it into a list of numbers, which we would call an embedding or a vector. And in several cases, it's really easy to do that. You know, I've got tabular data where I've got rows and columns, and each column has a number in it, and I take all of my columns and I smash it together, and now I've got an embedding. But how do we do that with a graph? Well, I'm going to show you that today. But before we do that, we actually have to create a knowledge graph, which is kind of going to be part of the meat of the course, is using machine learning and specifically natural language processing to create our graph of unstructured text. But we obviously have to have some text. So we're going to get some text. It's going to be fairly basic today. We're just going to be using things like Wikipedia to get our text, and text, for those of you who do natural language processing or NLP, or those of you who don't, text is very noisy. NLP is hard. And so we're going to see that noise reflected in our graph today. And we'll talk about ways that you can denoise it. The first half of the workshop is going to be dedicated to NLP. We're going to be talking about how you can turn that raw text into a graph using NLP. The second half is going to be some basic machine learning. We're going to be working with something called the Graph Data Science Library, which is built into Neo4j. That's not a requirement. It just is going to make things easier for us today. But you know, you can pick your favorite tools of choice as you get out of that knowledge graph and into these two things on the right here. Okay, now if you only take away two things from today's workshop, these are what I hope they are. First, when you're talking about natural language processing, there is no such quote unquote silver bullet. NLP is hard. There's a reason that when you look at job postings, you will see NLP experts specifically called out as, you know, a subdiscipline, but they're specifically looking for NLP experts. So NLP is hard. Second, like we talked about in the comic strip, the quality of what you get out depends on the quality of what you put in. We're going to be doing an admittedly very hacky way of creating a knowledge graph, just to kind of get you thinking about some ways that you could do this with different machine learning approaches. There's an infinite number of ways you can do it. I'm going to show you two different ways today, but just to kind of keep in mind how to get quality answers out of your knowledge graph. Okay, just really quick, what is a knowledge graph? It's all about, you know, a graph is all about just connecting things. So I've got nodes as circles. They're connected via edges or relationships, such as I have Leonardo da Vinci painted the Mona Lisa. And that's all well and good. I could use that for a question answering system. But I could use this knowledge graph for many other things. For instance, I have James here, who's kind of in the 5 o'clock position on the clock to the Mona Lisa. James likes the Mona Lisa. So we know that James has certain connections with Paris. He's visited the Louvre. He has lived in the Eiffel Tower. Here's an example of a knowledge graph gone wrong. Obviously, you don't live in the Eiffel Tower. We'll see examples of that in the data that we work with today. Now, here's the interesting thing. We see that Lily, who's located roughly in the 8 o'clock position on the clock, is a friend of James. Lily is interested in Da Vinci. Now, we might be able to build a recommendation engine with this knowledge graph and say, hey, if James likes the Mona Lisa, then maybe Lily likes the Mona Lisa, especially because she also likes Da Vinci. So we could use a knowledge graph as a recommender system as Lily goes to plan her vacation. Someday we'll get to do that all again. Okay, Google pioneered this statement, things not strings. And that's the whole idea of a knowledge graph is, we're not just taking strings and saying Lily likes Da Vinci and James likes the Mona Lisa. We are looking at those connections, and I'll talk a bit about why those connections are so empowering in data science here in a minute. What knowledge graphs are useful for? We can talk about search, question answering, recommendation engines. They can be used a lot of different ways. They can be generated in a lot of different ways, such as co-occurrence of words, resource description frameworks or RDFs, subject, verb, object. I'm only going to be using one of those today, the subject, verb, object model or SVO. But there's all kinds of different ways that you could do this. Now, let's just keep moving along here. Okay. So word co-occurrence, I'm sure we are all just ecstatically looking at yet another graph of COVID. I'm pretty sure we've all seen at least one similar graph. And what we're looking at here in particular is research papers that were published on COVID. And the size of the nodes that you see here reflect how many times words occur within this whole corpus of documents. So for instance, right in the middle, you see the big red one that says coronavirus infection. Obviously, that would be a very commonly used term in all of these documents. But then we see there is a close relationship between coronavirus infection and pandemic. Pandemic is also large. Now, they're close together because that means that those two words are co-occurring within a lot of papers. So you might expect if a paper says coronavirus infection, it would also say pandemic. The other thing about this graph is that you can see that it clusters. So there was a clustering algorithm applied here whereby you've got this red cluster, and that red cluster kind of describes the general terms. But then I have like the blue cluster on the lower left, and it's probably hard to read. I can tell you that the largest node there is SARS, and we do know that there's an epidemiological connection between SARS and coronavirus. And if you were to look at, if you could get that font bigger, you'd see that there's different proteins associated here and amino acid sequences and all that, and that's all well and good. The yellow on the top, those are describing people and fevers. So we have males and females, middle-aged, adult. We see fever, clinical laboratory techniques. So this is actually looking at the manifestation of the virus in people. So we have a few things going on here. We have the closeness of these nodes indicating how often they co-occur. We have the color of the nodes indicating how they cluster. And we have the size of the nodes indicating how often they occur within our corpus of documents. Okay, then we have this concept called RDF triples. So Resource Description Framework, that's what that stands for. It's a standard that was put out by the World Wide Web Consortium. And you can also think of these are also called semantic triples. But what this is this looks at how things are connected across the internet. So for instance, I have this kind of centralish node that says contact me. And we have a relationship that says Eric Miller. Okay, so the relationship label is full name, contact full name. So I can see that my contact me button is going to connect me to Eric Miller and the full name. And so this is just kind of like a standard format. We're not going to do this today, but if you're ever interested in getting involved with RDF triples within Neo4j, there is a package called Neosemantics that does all this for you. But today we're going to do something a little different. We're going to do subject, verb, object triples, SVO triples. You might also hear them called SPO triples, subject, predicate, object. But really it's the same thing. So we have sentences, and our sentences have subjects and objects. So for instance, I could say my subject is Da Vinci. My object is Mona Lisa. Now there's a verb that connects those things, and that verb is going to be our relationship. So in this case, painted. So Da Vinci painted Mona Lisa. So this is just kind of what our graph model is going to look like in a very basic high level approach here. Okay, but how are we going to get the subject, verb, object triples? I'm glad you asked. Okay. We are going to start with a concept called named entity recognition. Named entity recognition is that thing that's going to get us the subjects like the Louvre, Paris, Da Vinci, James, Lily. Okay, and we have some free automated tools for doing that built within Python. Today we're going to be working in Python, and we're going to be using Cypher as our query language. What we will find as we do this, though, is that when we can get the subjects and objects relatively easily, but the verbs are really hard. And you're going to see examples of that. Now, one of the things I'm going to tell you is, unlike a lot of people who are attending today, English is my first language, and I don't really speak a lot of other written languages. So what I'm going to talk to you about today is focused on English. There are packages that can, you can work with any other language really, but today we're going to be using an English language model. Lastly, NLP is very topic area dependent. And I bring this up because it emphasizes the need when you're generating your knowledge graph to have subject matter experts involved. So for instance, when we're looking at that coronavirus graph, if it were me, I'm not an epidemiologist or a physician or anything like that, so I wouldn't really know what I'm looking at here. I would rely on a subject matter expert who does have that field of expertise to say, this is a keyword that is not appearing in your graph. We need to make sure that it gets there. We will see an example of that today where the subject matter expert is crucial to have them involved in this process. Okay, before I do that, I just want to flip over really quick and see if we have questions. Let me make this one smaller. Okay, glitch in sound, audio. Okay, SVO triples is a term specific to Neo4j. No, it's not. This is just kind of a generic natural language processing knowledge graph term. And predicate and verb are semantically equivalent. So yeah, they're the same thing. It's the action that's being taken here. Okay, so I'm going to flip back now to my slides. I'm going to try to do this a few times where I go back and forth just so I can catch the questions as they come in. But one of the things I always like about doing this workshop is that it can be very interactive, not just with me and you, but among the participants, especially as we get live coding. So I really encourage you that if you see a question that comes up, dive into chat. Please help your fellow attendees. We all know that, online workshops in this age of pandemics are difficult. So, help me out, help your fellow attendees out. It'll be great. Okay, so let me go back to my slides. Okay. Back here. So I'm just going to give you an example of some text here, and I don't expect that this font is going to come across real well on your screen. That's not the point. The point is I've grabbed the Wikipedia summary of Barack Obama. And what I've done is I've done a named entity recognition here on and part of speech recognition to try and figure out what's happening in this text. So I just use this because it's nice unstructured text. It's not been cleaned at all or anything like that. And what do I have here? Well, Barack Hussein Obama II is that purple bubble that's in the upper left. And the package that we're going to use today, the open source software that we will use to do our NLP is called Spacey. And so Spacey generated this. And these are all the things that Spacey detected as being present here. So if you see that purple box, it says person if you can't make it out, but all of those little purple bubbles are people that Spacey detected. And then we've got kind of the cyan bubbles, and those are organizations. So for instance, I see the Democratic Party, I see the University of Chicago Law School, etc. So Spacey is capable of detecting what these entities are. There's dates in here as well. They're kind of like a mint green color. Okay, so that's going to be really helpful as we start this process of NLP. Okay. I'm going to take just that first sentence out of Wikipedia and just kind of explain how sentences get structured. Barack Hussein Obama II is an American politician and attorney who served as the 44th president of the United States from 2009 to 2017. Okay, cool. What you see below, the eye chart that you see there, is just looking at how words are depending on other words. Okay, so this is not a really super long bit of text here, but you can see we've got words, which are the little teensy tiny things, and they're connecting to other words. Let me zoom in a touch on that. And what I can see here is that words are connected to other words, which, you know, is kind of a neat thing in and of itself, because it means natural language processing in and of itself is graph analytics, which that's really cool if you think about that. But you can see that some words are based on multiple other words. But the one thing I want you to look at is if you can see the word is, and I've got stuff that's branching out in both directions from the word is. Okay, that's going to be important here as we start talking about the actual text. Okay, so here's that same sentence, and I've broken it up just as a table going word by word here. The first column is the raw text, so I haven't done anything with that. The second column is the lemma. The lemma is the absolute root of the word. So for example, you'll see that one lemma that's in the cyan, which is be. Be is the lemma of is. Okay, if you were to look down a little bit, you know, maybe 7 rows below, I see the word served, past tense. So past tense becomes the lemma serve. Okay, then I have tags and I have parts of speech, and those are just different ways of saying what kind of word is that word. But then I want you to look at the second column from the right, and those are dependencies. Okay, now the first thing that you see there, I've got it highlighted in big bold red, which should suggest that it's really super important, is the root of the word, of the sentence. That root is the most important verb in the sentence. We always want to find the root. Okay, everything else is going to be based on that root, but you'll notice it's not the only verb in the sentence. Served is also a verb. Okay, and we'll come back to why that's important here in a second. And then that final column is stop, meaning is it a stop word? Is it a word that adds nothing to the sentence? The word the, for instance. I don't want to sit here and count the word the every time it comes up. It doesn't provide me any useful information. So we can get rid of stop words as part of our NLP process. Okay, now I want to draw your attention here to this blue box that I just added, these dependencies. You see I have a dependency 4 rows down that's called N sub. It's the noun, it's the subject noun of the entire sentence. And unfortunately, it comes up with the Roman numeral 2, which is not entirely correct. But then I have these compounds before it. And what we can do is we can take that N sub and grab every immediate compound just before it, and that tells us our named entity. So in this case, Barack Hussein Obama II can get all lumped together just by the fact that I have compounds immediately preceding that subject verb. Okay, let's look at another one here, because it's not the only object. It's not the only noun that we have here. For instance, I've got united as a noun and states as a noun. So I have P object, and that's just the object of my sentence. And I have a compound right before it, which says we want to lump those things together as well. Okay, so then I would wind up with my subject, Barack Hussein Obama II. I would have the verb be, and then I would have United States. But that's not quite right, is it? So we actually have to get a little sophisticated here as we do this. And so I'm going to pop out of my slides here for a second, and I'm going to ask you a question. So I'm going to pause my sharing. Okay, I'm going to try pausing my sharing. And what I want to ask you, you've seen this sentence now. How might I determine which verb applies to United States, that object in the sentence there? So I am looking at Barack Hussein Obama be United States, or Barack Hussein Obama served United States. So take a minute and type into chat how we might do this. There's no one correct answer here. Just go into chat and let me know what you think. And Akbar, I would like to thank you for that question about the differences between verbs and predicates. Okay, so don't be shy. How do you think do you think we might be able to grab the correct verb for the object? Okay, I see some people are typing, so I'm going to give it a minute here for your answers to pop up, and then I'll tell you how I did it, albeit hacky. Using proximity and position in some way. Yeah, like it. When you do it like I do it, like adjacency, I see that one. There's, we've got all kinds of NLP tools out there. Like I said, I'm going to use Spacey, but there's some pretty sophisticated ones out there. I will throw out an acknowledgement to BERT, which is a transformer model based on the tree of the dependency parser. Like that. Definitely can do that. So, okay, so I'm going to tell you just really quickly how I did it in a hacky way. So, let's see, statistical correlation. Ooh. Okay, how do I get back? I see, unpause sharing. Okay, so hopefully y'all are seeing my slides again. Elias, if that's not true, let me know. Okay, so the way I did it, and the way you'll see it in the code today, admittedly hacky, and there's some very sophisticated statistical answers that are coming out in chat. I took the object of the sentence and I found the closest verb in proximity to it. So in this case, that would be serve, but you'll see there's going to be other bits of text here that will result in Barack Hussein Obama be United States. So this is part of text being noisy. Okay. All right, let's talk a little bit about the tools we're going to use today. I mentioned Spacey. Spacey is a nice open source Python package for doing all kinds of very sophisticated NLP. And I also said that I was grabbing text from Wikipedia. So there's the Wikipedia Python package that we're going to use. But also we're going to play around a little bit with the Google Knowledge Graph. Now we don't have time to actually go and create our our APIs for querying the knowledge graph. I'm going to provide you with that data today. And is it necessary? No, it really depends on what text and what data you have at hand. I'm just going to use it today to enhance the data that I'm bringing in, just to kind of make a few points here. I'm going to show you two different methods today to create a knowledge graph from raw text. So Google Knowledge Graph with Wikipedia, but then PyWikiBot. And so, I'm sure that a lot of you have had this idea of we could use Wikidata or Wikimedia. And yes, we absolutely could. There's a bot that you can use for querying Wikidata called PyWikiBot. You need an API to run it, but it's all good. It's pretty straightforward. Okay, when we actually get into using the graph database Neo4j, we're going to use a few tools that are built in. First, awesome procedures on Cypher or APOC. Cypher is our query language, you see at the bottom bullet, but APOC is kind of like this really nice add-on, and I've heard it said that if you can't figure out how to do something with Cypher, go look at APOC. It probably exists there, and that is true. And then the last thing, we're going to do some machine learning on this graph. In order to do that, we're going to use this library called the Graph Data Science Library, and you'll get a feel for what that means in a minute here. Okay, as a reminder, here's where the repository is for all of the code that we're going to be using today. Okay, so you can choose to code along, you can choose to just watch, it's all good, whatever floats your boat. Okay, so I mentioned today that we're going to use two different methods to create a knowledge graph. The first, method one here, I call the NLP only approach. And so what do I mean by that? So basically, this is a very high level view of what we're going to do is we're going to clean the text. I like to say that data science, 80% of data science is data janitor, really. So everything is cleaning. Once we clean that text, we're going to get all the named entities, and then we're going to create that subject, verb, object triple for each named entity. Using Spacey to detect those parts of speech, find the nearest verb to an object, things like that. If we wanted to get really sophisticated, I'm not going to do it today, but you could get some adjectives associated with each of those subjects and objects and use them as, say, node properties in your graph. And then we're going to assemble the graph. So that's how we're going to create our graph using NLP. The advantage of this approach is that it has limitless verbs. If I can detect the verb, I can put it in my graph. So whatever relationship I detect can go in there. The problem, as we're going to see, is entity disambiguation. And basically what that means is I've got two nodes that really are the same thing, but it's coming back as separate. Okay. I just want to talk a little bit about how we vectorize. And in particular, we're going to start talking about vectorizing text. We have this thing called word2vec. It's a pretty common method of vectorizing text. Why do we need that? Well, because the only thing I can put into a machine learning model is numbers. So I have to find a way to turn text into numbers, and word2vec is a pretty popular way of doing it. It's a skipgram approach. It tries to determine the meaning of words that are not being blacked out. So I black out a word and I try and figure out, what meaning does that have? And I do these weights and biases, and eventually what winds up happening is I get a vector of floats. Okay, so it's like a list of floats, or you could put it in tensor format. So here's a little sentence that we did that with. It gave a research talk in Boston. Okay, cool. So removing the stop words, it's kind of hard to see that some of those words are bold-faced and some are not. Now, that's one sentence. I'm going to compare it to the sentence all the way on the far right, had a science lecture in Seattle. Okay, so now what we're going to do is we're going to use word2vec to create vectors, and then I can plot that out in a two-dimensional space through some sort of dimensionality reduction. And what I can see is words that are very close to each other in meaning. For example, Boston and Seattle. Makes sense that those would be close to each other in this plot because they're cities. Research and science. Lecture and talk. But I see that lecture and Boston are not close to each other because their meaning is very different. Okay, so that's how we could use word embeddings to learn something about our sentences and our text. Okay, let's talk a little bit more about what happens when we get that text, what this workflow is going to be. Just today, I'm going to use just Wikidata. I'm going to grab summaries from Wikidata for a given search term. And we're going to do NLP on that text to get all of the SVO triples. Okay, so once we have those SVO triples, we add them to the graph. And what we do then is that we can add node labels and properties based on what we might figure out from those subjects and objects. I'll show you how we're going to do that with the Google Knowledge Graph here in a second. And then there's our cleaning process, dedupe, clean, dedupe some more. And we're going to be deduping till the cows come home. But once we have that, we have a nice graph, and then we're going to do our machine learning on that graph. And the first thing that we do is we create a projection of the graph. We call it a graph projection or an in-memory graph. It's taking a subset of the graph that we care about to do math on. Using that in-memory graph, we generate graph embeddings, and then we do some machine learning on those graph embeddings. Okay. Just a little bit more on the real nitty-gritty about the NLP portion. We're going to remove control characters and regex. That's part of our cleaning. We use Spacy to create what they call a Spacy doc, which is how Spacy interfaces with the text itself. We get those subject, verbs, and objects. We find the closest verb to each object. We also do some more cleaning with removing stop words and punctuations. We assemble our SVO as a tuple. We dedupe that tuple, and I got rid of dates just because I didn't find them very helpful. Okay, so I want to just pause right here. I am going to stop sharing my screen and check in just to see if there's other questions. Okay. So I'm scrolling up using semantic. Okay, for APOC, do we need the full or the base? We're going to be just using, the standard out of the can APOC. It comes pre-installed in Sandbox, so you're not going to need to worry about that bit. That being said, with the code that's in the repository, I have it also set up where you could run it on your own local machine through Docker, and it will pull in just full-on APOC as you stand that up. The instructions are in the README in the repo, as well as the Docker file, the Docker Compose file, and the package requirements. Thank you, everybody, for posting the GitHub repo. Okay, so let's go back into our slides. Okay, slides, here we go. All right, now I mentioned before that we were going to use the Google Knowledge Graph, not because we're using it to create a knowledge graph. I'm just querying it to make the knowledge graph we're going to create a little bit more interesting. In order to do that, if you wanted to do this on your own, you need to create an API key for it. But that API key is like, you get something like 100,000 queries per day for free. So it's pretty robust. It's pretty, gives you a lot of calls per day. Not required for today. I just want to, put it out there that that's how we are doing this today. When you query the Google Knowledge Graph, this is a bit of what you get back. So in this case, I queried for Taylor Swift. Now, I will admit to knowing nothing about Taylor Swift, so bear with me here. But I get back the name. Okay, so I get back a name, which is basically my search term. And then I get back something called type. These are interesting. The type can be used, if we do it properly, to create our node labels. So I would have Taylor Swift labeled as a thing, could be, and a person. And that's helpful as we want to query our graph, especially as the graphs get big. The more you can say about your query term, like if I said I'm looking for persons named Taylor Swift versus I'm looking over my entire graph, that makes your queries faster. Okay, and then I have this article body, which is Google's way of giving you a sentence or two description about this person, or whatever this search term was. And then I have a URL. I'm just going to use those to populate the graph, not because we're actually fully using them, but just to give you a feel for a way that you could create this graph. Okay. Once we have that, we're going to use that information, and this is our graph model. So we have our subject, and our subject has a property called name. So like that would be Taylor Swift. Then there's a verb, which we have to go detect. And then we've got an object, and my object is going to have a property called name. And the objects also have the node labels. So let's say somebody was friends with Taylor Swift, and we know Taylor Swift is a thing and a person. So then we get this list of node labels, thing and person. We get the description, which is that sentence or two back, and we get the URL. Then what I'm going to do just for fun is I'm going to use Spatie to create a word vector, a word embedding based on that description. Okay, it's not going to be 100% useful to us today, but I'm putting this out there just for your future knowledge graph use, that I'll show you how it might benefit you in your graph embeddings down the road. Okay, now the other thing I do want to mention is that when we query the Google Knowledge Graph, it doesn't necessarily have all of this information. It doesn't necessarily have node labels or descriptions or all of that. So you get what you get and you don't get upset. That's what I tell my kid. Okay, when we do that, this is what our graph is going to finally look like using this method. I don't expect you to be able to read it, just kind of get a mental idea of what it looks like. My node labels are represented by different colors here. You'll see this more in depth as we actually start the coding process. Okay, I mentioned before that we're going to have two methods, and I call this next one the NLP Lite approach. And what do I mean by that? Well, we're going to be querying Wikidata based on the named entities that we find in our text. And when we query Wikidata, it's really nice because I have these things called Q codes. And what Q codes are is the subject of my sentence. So in this case, you can see Douglas Adams here has a Q code of 42. If you know Douglas Adams and his writings, that's actually kind of funny. So I have a Q code of 42 associated with Douglas Adams. Then I have a P code. P code is the property. So you see here, educated at, in that purple box is the property. And really what that is, that's the verb, right? So then what are my objects? Well, my objects are the values associated with that property. So St. John's College, it's that thing in orange. So automatically I've just assembled, a subject, I have a verb, and I have an object. And that's really cool. So what we're going to do, again, clean the text and get the named entities, but then we're going to get Wikidata items and claims for each entity, and we're going to assemble our graph that way. This has a really strong advantage of entity disambiguation. Okay, you will find other entities in the graph in the Wikidata called Douglas Adams, but generally speaking, it's going to be obvious which one the right one is, and I usually just go with the first one or the lowest Q value number. The drawback, though, is that I actually have to specify what my verbs are. You remember in method 1, we have limitless verbs. In this method, we don't. We have to specify the P codes that we care about. Okay. When we do this, again, this is not required for today. This is if you wanted to run the code on your own and create your own knowledge graphs. There's all kinds of different ways that you could get data out of Wikidata using Python. But one of the most common ones is this thing called PyWikibot. It's just a bot that goes and scrapes Wikidata. You have to have an API for it, which you would get through this process. You create yourself an account on Wikidata, and then using that account, you can go in and create your bot. Okay, so when we do that, here's the graph model that we're going to have using Wikidata. We have our subject and object again. Each of my nodes will have a name. It will have an ID, which is the Q code, and it will have a type, which is instance of. So like if I'm back here, is instance of is not on this screen. But there's a particular P code. It happens to be P31. I know that because I've looked at these a bunch. And it would say Douglas Adams is instance of human. Okay. Okay. So then my claim, this is the jargon of Wikidata. Claim is what they would call a verb. A claim has a P code. Okay. So that's just the language that they use with Wikidata. Okay, when we do that, we're going to be using the very same text and search term, and this is the graph that we're going to get. And so it's a little bit more rich. You can see that there are a few more nodes. What we're going to find, the previous graph is something like 830 nodes, and this one's going to be something like 1,400. You'll see what happens when we start doing question answering on this. Okay, and then the last thing that we're going to do is machine learning on the graphs. Now, this is a subject that's near and dear to my heart, and I'm going to tell you why. When we talk about traditional machine learning, we have an assumption, and that assumption is I have rows and columns, and my rows correspond to I have this item, and it's got this vector, and I've got this item, and it's got this vector, and there's no relationship to them. It's one of the tenets of machine learning is the independence of our data points. Okay, however, it's not always the best way to look at it, it turns out. Graphs and graph databases, doesn't matter which one you use, they treat the relationships as the first-class citizen, not the nodes, so not my individual rows, okay? And this is important for this concept called homophily, which basically says that when we have entities that are similar, they should be closer together in the graph. Churn prediction is a great example of that. For example, if I was Barack Obama and Michelle Obama decided to leave Facebook, I have a higher probability of leaving Facebook. Let me give you another example. And you see I have this picture of a mailbox down in the lower right-hand corner. I said that knowledge graphs could be used for recommendation engines. So the reason I have a mailbox here is because a few years ago, I built a house that I'm speaking to you from high in the mountains of Colorado. And so you can imagine that we spent a fair bit of time in the hardware store, and the hardware store could kind of learn the type of person and what I might be doing by looking at what I was purchasing. So they saw that I was purchasing a whole bunch of wood and nails, and they said, oh, maybe Claire's building a house. And then they watch what I'm purchasing next. I'm purchasing wiring and pipes for plumbing, and then I start purchasing drywall, so they can kind of get a feel of where I am in this home build process. Now, this is a true example, okay? I have not made this one up. This is for real. Big box hardware store that shall remain unnamed. They said, hey, Claire, you should purchase a mailbox because it looks like you're getting towards the end of your build, and people who are building houses usually towards the end of the build buy a mailbox. But I didn't. And why didn't I? Well, it turns out that where I live has no mail service. I have to go to a post office box in town to get my mail and my packages. Okay, but let's look at all of my geographic neighbors here. None of them bought mailboxes either. Okay, and for the very same reason. Now, if they considered that I lived near all of these people and that none of them bought mailboxes, then they might not be recommending mailboxes to me. And especially also because they had my zip code. True story though, said big box hardware store has a whole row of mailboxes waiting for people in my area to buy them, and nobody is. It's collecting dust because they did not consider the relationships between the data. Okay, so machine learning with any graph, but knowledge graphs today, is a really powerful tool that can really enhance the accuracy of your machine learning models. Now let's talk about how this works. You remember we talked about word-to-vec, which was this skip-gram approach, and it goes sequentially through a sentence. How do you go sequentially through a graph? That's a little bit more complicated. You know, what do I do? Well, in general, what I do is instead of going sequentially through things, I randomly hop around my graph. So like we had word-to-vec, we have an analogous node-to-vec. And node-to-vec is pretty cool. You have your central node here, which is listed as V, and I could hop to any one of these other nodes. And I have a certain probability if I'm at V of hopping to my different nodes, and that's represented by alpha. Alpha is a function of this thing called Q or P. P stands for the return parameter, and so what that return parameter says is if I hop out, what's my probability of hopping back? If I have my Q value, that's my walk away parameter. So that determines how likely I am to move across my graph. Now, for those of you students who are attending today, here is a great interview question. Frequently, students in any branch of software engineering will get asked, write me a breadth first search algorithm or a depth first search algorithm. Well, you can do that with graphs. So for instance, breadth first search, you would want a low value of P, and depth first search, you want a low value of Q. So this is how you can create a search algorithm to amaze and stun your interviewers using graphs. Okay, cool. When I do that, when I run node-to-vec on a graph, I don't expect that you can read this, but I have a name, you know, like my subjects or my objects in the graph, and then I get these things, these graph embeddings, and they can be however many dimensions I specify. In this case, I specified 10. Okay, so these are 10-dimensional graph embeddings based on just hopping around that graph because relationships are important. Okay, and anything that we would do with machine learning on normal embeddings, we can do with graph embeddings because all I have is just a list of floats. So list of floats can be thrown into anything, such as node similarity. I could do some sort of cosine similarity between, you know, different nodes in my graph, and, you know, we could do any number of things. I can also take those embeddings.
Here.
Yes.
There is a question that
okay.
should be addressed now. From Michael Scott, can labels be nodes or are they arbitrary input?
Okay. Labels specify what the node is. So like Barack Obama is a human. Washington, D.C. is a place. What you're going to see how I do this is I start by saying everything is a label type node. Okay, that's kind of cheesy, but I don't start by caring exactly what they are, but it obviously is it matters to us. It helps us with our understanding to be able to say, I'm looking for all the humans in this graph and which humans are connected to which other humans, or how is a person tied to a place for like a question answering system. I'm going to give you an actual demo of that exact question when we get into the code. So I hope that helps. Okay, so then another thing that we can do with our embeddings is that we can do some dimensionality reduction to look at them and see how well they cluster. So here's, this is just one approach. This is T-distributed stochastic neighbor embedding, or TSNE. When you deal with embeddings, you always like to see, like I have cases of 0 and cases of 1, and we really like to see is that all of my zeros are clustered together and all my ones are clustered densely together, and the separation between the two is great. Okay, we do that with normal machine learning algorithms, and we can do that with graph embeddings as well. Okay, let's get this party started. I am going to give you just a minute to write down the GitHub repo address. If you scroll up in chat, other people had posted that in there, but we're going to actually do this now. Okay, before I actually do this, I'm going to come back. I'm going to pause my sharing here. I'm going to look at, are there any more questions? And I don't see any. Grab a quick drink. Okay, let's what I'm going to do is I'm going to walk us through the repository right now, just so you can get a feel for what's in here. Okay, so hopefully you're seeing my repository. Elias, let me know if that's not true. Okay, yeah.
We can see.
You do see it?
Yes.
Okay, cool. Okay, so this is just our repository for today. And of course, we should start with our README. Okay, I have links to what we're going to be using today, Sandbox and Google Colab, but you could also be running this using Docker. Those files are here. I'm not going to talk about how to do it today, but the instructions are in the README. Okay. In particular, the Neo4j sandboxes come in a few different flavors. We're going to be using a blank sandbox. We're also going to use a blank graph data science sandbox. Okay, so just those are two different ways, two different types of sandbox. The blank graph data science one is kind of a hidden special sandbox, so you just got the super secret promo on that one. But let's talk about the code. Okay, we're going to see the code in a few places. First off, I have notebooks. Okay, these are the things we're actually going to be using in Colab here. We're going to pull these notebooks in. And, you can click on them. They have, assuming GitHub wants to render them, there's a whole bunch of comments in here about how they work. So you can read through those on your own time. Then, other than notebooks, we also, and I'm going to be jumping around in this repository a lot. This is where we're going to start running pretty fast. We have a folder called Cipher Queries. Okay, and I have starting queries. These are going to be how we populate the graph. And there's also a few helpful, like how to view all the nodes in this graph. I'm going to talk you through some Cipher here in a minute, so don't worry if that looks foreign to you. And then I also have method 1 and method 2 queries. So those are the two different methods that we've talked about today. And then the other thing I want to point out is this directory called slides, because everybody always asks, are the slides going to be available? And yes, absolutely, they are available. So the Google slides that I was looking at before are in this PDF file, but I'm also going to show you some HTML slides that are rendered based off of the notebooks. Okay, so let's dive right in. Okay, we're going to get started with method 1. Now, method 1, if you recall, was that big NLP approach that you could get all the verbs, but it's kind of noisy. Okay, so we have typical imports here. We need to configure spacey. Now, I do want to say something about this, because the spacey named entity recognition is a function of which vocabulary do you pull in. And the vocabulary can come in a whole bunch of different sizes. The one we're going to use today is this English Core Web MD. So what this is it took basically the entire web in English, and they created MD, a medium size vocabulary out of it. There's also a small size vocabulary, there's a large size vocabulary, but there's a catch here. Like you might say, hey, I should just get the small one. The problem is that those word vectors that we're going to be using do not fully exist in the small library. So at a minimum, you want to use the medium one. Okay, I mentioned that we're going to be querying the Google Knowledge Graph. We want an API key if we're going to truly do this from the get-go. Okay, and this is just how we set spacey up. We tell it what vocabulary we want it to use via this, this spacey.load thing here. I add to my pipeline this thing called merge noun chunks, and what that is, that's the named entity recognizer of spacey. I'm also specifying some of my parts of speech that I'm going to say, these things are all subjects, these things are all verbs, and these things are objects. I use a few labels here. And this is just going to help us set up our SVO triples. Okay, so querying the Google Knowledge Graph, we get our API key. There's a function in the notebook called query Google, and it's just set up to make this kind of simple, return the information that you want. And then a whole bunch of helper functions here. These helper functions are for cleaning the text. So remember I said clean, dedupe, dedupe some more, clean some more. Okay. So the heart of the matter, let me actually go into the, nope, that's what I just had open. That's not going to work. I am going to go into the notebook really quick And you can see that all of these things are actually in the notebook. Let's scroll down though. Okay. The main crux of the matter here is this function called create SVO triples. Okay, this is the thing that's going to create the tuples of subject, verbs, and objects. Okay, and as we do this, what we're going to see here, we're going to start with text, and I'm searching Wikipedia for Barack Obama. Got to start somewhere. And this is just the summary, which is, the paragraph or two that's at the top of the Wikipedia page. This is just giving us raw text, whatever you want to use to get raw text, totally cool. I have some helper functions here for getting the object properties. So the objects, we're going to get things like the labels, thing or person. In the case of Taylor Swift, we're going to get the descriptions, we're going to get the URLs, things like that. And then what we're going to do, a little bit of cleaning here, we're going to get our spacey word vectors for each of those descriptions. Okay, so if I were to run this, and I'm not going to actually run this part today because it can take a little bit of time. So I'm just running, I'm creating a tuple list using that starter function, create the SVO triples using that text. Okay, and if I look at that tuple list, here's the first 3 entries in it. I see the phonetic spelling of Obama is the first one, which is always exciting. And then I have B. Okay, that's my verb. American politician. Yay, the first one is right. Obama B, 44th president. Huzzah, life is good. But then I've got the one I warned you about, Obama B, United States. Okay, so remember, text is noisy, processing text is hard, and there is no proverbial silver bullet. Okay. I have this thing that populates my relationships. And these are just kind of how we add to our tuples. So you can recognize our first few tuples. So here, here's my object, and it turned out that Google Knowledge Graph came back with a description, which we'll use. And then it came back with a whole bunch of node labels. Okay, so these are the types that the types of the nodes. So United States could be a thing, could be a country, could be a place, could be an administrative area. The good news is that we can say that that node is all of those things. We don't have to pick and choose. We assign that same label to all of them. Okay, so then what we have our node lists and edge lists. Those are the 2 things that you really need for any graph database to populate it. So a node list would contain something like, here's my node and all of the properties associated with my node. Okay, and then it usually has some sort of unique identifier for my edge list. So my edge list would say unique identifier 1 is connected through this type of relationship to unique identifier 2. Okay, so that's basically all this code is doing, is creating node lists and edge lists based on Google Knowledge Graph and spacey. Okay, eventually what happens is we are going to populate the graph. We're actually going to do that in one of the next notebooks here. Today, I'm going to show you 2 different Python packages for doing that. There is the official Python driver for Python. It's called Neo4j, cleverly named. But there's also a community one called Py2Neo. And so I'm going to show you how to use both of them today. At the end of the day, though, whatever you want to use, they both work, they both return their values in kind of different data formats, and you just pick and choose which one you like best. Okay, so we're going to go through this whole process of entity disambiguation. I told you this is going to become a problem. You're going to see it when we start running code here. Entity disambiguation is going to say things like, is President Barack Obama the same thing as Obama with the phonetic spelling? Okay, we're going to start by doing that with traditional NLP. Remember, I said that we were grabbing those word vectors for the descriptions. So I can do cosine similarity on those word vectors. For instance, if I do cosine similarity on the word vectors for the Barack Obama node and the President Barack Obama node, what we see is that I have, a very high similarity, which is good. But that one's kind of cheating because Google Knowledge Graph is capable of saying Barack Obama and President Barack Obama are the same thing. So let's pick, even if I picked Barack Obama and Mitch McConnell, which if you know anything about politics in the United States, these guys are bipolar opposites. And what we see here is we still have a pretty high similarity. And that's probably because they share a lot of things in common. They're both politicians. They both attended Harvard Law School. They both work on different legislations. They've both been in the Senate. So it's not entirely surprising that their similarity is high. Okay, now if we were to do this, if you run the code in this notebook, notebook 0, okay, what we see is we're missing a key person here. If you look for somebody in this graph whose name is Michelle, you will not find her. Okay, this is an example of when you want the subject matter expert involved. You want, in this case, we're all going to play the role of subject matter expert on US politics. We know that Michelle Obama is married to Barack Obama, and yet she's not in this graph. So we have to raise our hand and say, hey, knowledge graph people, we're missing a key node here. We need to add this to our knowledge graph. Okay, so in the next notebook, which is notebook 1, we build that out a bit more. And you can scroll through, let me just do this instead of the slides. I'll do this in the notebook itself. We can scroll through, nice. I'll just go to the slides then. Okay, so this is exactly the same stuff as before, but all I'm doing here, I make my connection again, same as before. And all I've done is I've added one query for Barack Obama and I've added a second query for Michelle Obama, and they will connect to each other. It's kind of convenient. And I'll wind up with 863 nodes within my graph. I'll add them to my graph, and you can see this all happen within the notebooks themselves if you want to run them yourselves. Okay, but let's actually run some code finally. Okay, we are going to be using Google Colab. So you need obviously to have a Google account to do this. And what I'm going to do is I'm going to click on New. I'm going to click on More. Okay, let's see if I can get this to show up. And there's this Google Colaboratory thing here. So we're going to click on that. Okay. And what we're going to do, actually, let me start something else running here really quick because it's going to take a second. We're going to create our notebook or our database. Okay, so to create our database, our starting database, we go to sandbox.neo4j.com. And again, that's linked in the README and the repo, so you don't have to remember that. Okay, so what happens when I get that is I have this screen come up. It might ask you to, authenticate to like your Google account or something like that, but I have this screen that shows up. And I have a whole bunch of different types of databases that we can create. Some of them are pre-populated and some of them are not. But we're going to start with a blank one. Now, if you're unfamiliar with Neo4j, you're unfamiliar with Cypher, I really recommend this movies database because it walks you through a kind of like this nice introduction to Cypher. Okay, but we're going to spin up a blank sandbox for today. We're going to create that. So I clicked the create button in the lower left, and this is going to take a second. Okay, so while it does that, I'm now going to click the open button, open with browser, and we might get an error here. It might take it a second. You see it's taking a second right now. I should get a green scroller bar across my screen. If I haven't gotten that, it just means that it's still spinning it up. So don't worry, just give it a try or refresh later. But while we're waiting for that to happen, I've now gone back to Colab. Okay, and here's what I'm going to do. If you haven't seen, if you haven't worked with Google Colaboratory before, or maybe you haven't seen this, you can actually bring in GitHub repository notebooks into these things by clicking on this GitHub tab here. I'm going to come over here and I'm actually going to just grab the link so I don't type it wrong. So I'm just copying and pasting the link to my GitHub repo. Cool. And so what we see here, I have a whole bunch of different notebooks here. I'm going to open number 2 though. Okay, and I'm going to click this little open notebook and new tab thing just so I don't have to type that repo address out every time. Okay. And now that that's going, now let's see if we can open our sandbox and start creating a graph. Okay, so I see I have my green scroller bar, so I know that the instance is getting ready, is up and running, which is good. While it gets up and running, I'm just going to pause my sharing really quick and just see if there's any other questions. Okay, looks like people are getting their questions answered, so that's awesome. Okay, so I'm going to go back into my sharing. Okay. Sometimes I find that if you click away from the Neo4j browser tab, it gets a little cranky. It says, I want to have all of your attention. Zoom in here. Okay, so this is what the Neo4j browser looks like. It's just a nice convenient way of doing queries in Neo4j, but anything you can do here, you can also do in Python. With the exception of visualization, visualizing graphs is a little challenging. And I'm not going to talk too much about that today other than to show some examples. Okay, I can click on this button here and I see that I have an empty database. There are no labels in this database. There's no relationships here. So we have to start by populating my graph. Okay, and what I'm going to do, I have these JSON files in our repo. This is what we're going to use for populating our graph today. I am going to go into Cypher queries and starting queries. Okay, and what I'm going to do, we're going to start with the SVO graph. That's the method 1 graph. So I'm just going to copy and paste line 22 into my browser window. And this is going to take a second. Okay, so while it does that, I'll tell you, you might actually get a timeout error here. If you do, just check over here, because what I've noticed is that sometimes pulling data down from GitHub can be a little slow. But if you see like 800 some odd node labels showing up here, you've got your graph. Okay, so let's just give it a minute here. And while we do, I'm going to multitask. I'm going to come to Colab here just because we need to install, Colab comes pre-installed with a lot of useful things, but none of them involve any way to connect to Neo4j. So here I'm going to connect to Py2Neo, which is that community driver. Yeah, it was not authored by Google. I get it. Run it anyway. Okay, so we're installing the driver right now. We'll just let that run. It doesn't take that long. But here we go. Okay, we've got now some stuff that's loaded in. Okay, so I can see I have 862 nodes and I have 823 relations. Cool. Okay, so what can we do with that? Let's go back to our repository, and I am going to go back into the Cypher queries subdirectory, and I'm going to click on method 1 queries. Okay, so this is, let's look at our graph. So that's line 9. Now let me tell you a little bit about Cypher here. For those of you who in the room are like more fans of SQL, this would be like select star and return everything from your database. When I see things, Cypher kind of looks like ASCII art. So when I have round parentheses, that indicates a node. Okay, like nodes are circles within the graph, right? So round parentheses, I say I'm going to match all nodes and I'm going to give them just a variable called n, and I'm going to just return all of them. So let's see what we get when we run line 9 here. Okay, so let's run line 9. Minimize that for a minute. Okay, whoa, I have a graph. Okay, I'm going to zoom out a little bit. I can scroll around, I can see what this graph looks like. All of my nodes are one color. You see they're all type node because I haven't done anything with them yet. Okay, now let's say if I click on the table button here on the left, no, that's probably a bad idea. Let me just go, I'm gonna match node, return that variable n, and I'm just gonna limit it to 1 just so we can look at it. Okay, so here my node is that phonetic spelling of Obama. I don't have a description. I have a node label of subject, which is just what I gave, you know, the query subject. You know, you can call it whatever you want. I have my word vectors. I made those word vectors 300 dimensional. Okay, so let's get to the bottom here. I have no URL. Okay, so that's each of my nodes is going to look like that with all of their node properties. Okay, one thing I want to tell you, I showed you that graph visualization. If you find browser starts running a little slow for you, one of the reasons is that those visualizations can take up a fair bit of memory. But if you click on this X over here, you can close that visualization. It might help. When in doubt, just refresh the browser and it should perk back up for you. Okay, cool. So what's our next query on the list? Okay. You remember I have a node label of subject. But I've just imported everything as a node label of node, and I can see that here with my node labels. Okay, I just have that orange node. But we have more information. Remember, we had things like Taylor Swift was a thing and a person, and we actually want to now make nodes that look like that. Okay, so let's do that. And in order to do that, we're going to come down and we're going to use lines 12 through 15 in method 1 queries. And I'm using a thing, APOC, add labels. So every, basically I'm matching a node, a variable name is n, and then when I have this colon here, colon node, that refers to the type of my node label. Everything has node label of node right now. And now we're going to make it a little more interesting. So every n has a property called node labels. It might be empty, okay, but I specify properties this way, n.node labels. Okay, and then I'm just going to get I'm going to just do that to all of my nodes. We're going to be moving pretty quickly through Cypher today. I apologize. There's all kinds of great Cypher learnings, like if you were to do that movies database, there's also Graph Academy where you can go learn a lot about Cypher. So let's just go add all these labels. What's going to happen here is you're going to see this thing over here, this node labels thing on the left is going to explode. Whoa, Nelly. Okay, I've got all kinds of nodes showing up here. Let's actually look at it because it's kind of cool. Okay, so I'm going to go match n, return n. Okay. Visualization of graphs can get a little cumbersome. If you start having a lot of nodes on the screen, it kind of looks like a cat, just, you know, you have a fur ball on your screen. The default limit here is 300 nodes, but we also know that there's like 800 some odd nodes in here. Okay, and what we see is that my node types are all labeled different, or the colors correspond to my node label. So I have my subject here in the middle, Barack Obama, and that's kind of like that teal color. I have things, which are in red. Now you'll find out that they're not always accurate. Like I see Hillary Clinton is a thing. Just like Taylor Swift was a thing. I have administrative areas, which are in pink. And if I scroll in, it actually does a fairly decent job on administrative areas. I've got Afghanistan, Iran, Libya, Hawaii is way out here. Organizations, kind of hit or miss, but we now have a graph to work with. So cool. Let's do it. How many Obamas are in the graph? Okay, so let's... this is a way we can specify, you know, I'm going to look at all of my nodes of type node, and I want that node to have a name containing Obama. And I'm going to just return all of those. Let's see what we get. So I'm just going to copy lines 18 through 20 into browser. Oh gosh, I have a bunch. So I have Obama terms, Barack Obama, Obamacare. I have a lot of Obamas here, and some of them are the same, Barack Obama and President Barack Obama. I told you entity disambiguation is going to be tricky, right? So I need to speed us up here just a touch. We have duplicates in here. I'm going to quickly show you how we can detect duplicates. And let's see, we're going to basically look at something similar here. We're going to look at our names, collect name as names. Okay, I have my nodes, and I want to see, I'm going to collect all of the n, that basically makes a list. Okay, and so I have a list of nodes. I strongly recommend you look at how Cypher works on this. If you go to the README, I have all kinds of Cypher cheat sheets and whatnot in there. And it'll just help as you learn Cypher more. But so basically I have a list. The list is named nodes. If that list is greater than 1, then I have a problem. So let's look at that. Oh my goodness. Okay, I have 20 cases where I have Barack Hussein Obama II. That is not good. Remember I said clean dedupe, clean dedupe. Now we're deduping even more. Okay, so how I'm going to dedupe is I'm going to drop my duplicates using lines 27 through 30. Okay. I'm just going to copy and paste those in here. And basically all I'm doing is the same thing. And I'm saying if the size of that list is greater than 1, then detach delete. Detach delete is your command to get rid of nodes and relationships. So I'm Okay, we got rid of 205 nodes and 265 relationships, so we still had some deduping to do here. I'm not going to show you some of these similarity metrics because I already showed them to you in the slides. We're going to do a machine learning problem now, to which you're all saying, oh my goodness, thank God. What we're going to do is it's going to be a multi-class problem. We're going to try and determine person, place, thing, or unknown. And what I have here is I'm going to set a node property. So for instance, I'm going to set this PPTU, person, place, thing, unknown, underscore person equals to 1 if my node labels contain any of these things, person, organization, blah, blah, blah. These are just kind of arbitrarily chosen by me. So I'm just going to do this really quick. We're going to copy lines 46 to 65. And what we see here, I have semicolons because I actually have multiple commands here. That's how you can separate multiple commands in Cypher. And you see this, it runs them each individually, and you can see a check mark when it's done. Okay. So now I need to also set my unknown. So there are some labels that were actually called unknown. So I if there was no label, we're going to set PPTU unknown as unknown. Okay, so here's what my unknowns are. Let's just look at it in table form. Oh, I didn't return it in something useful. Okay, so like, what was this one? Okay, I don't want to spend a lot of time scrolling through this, but here's one, March Senate primary win, and my node labels were empty. So this is an unknown. Okay, so we just set the node label as unknown. That's all we just did. Okay, now we get to actually do some data science. We're going to use the graph data science library. And if you recall, before I said that we're going to use these graph projections. What this is a very memory efficient way of doing math on these graphs. And we use this call GDS graph create function. We start by giving it a name. Our little in-memory graph is going to be called all nodes. Okay, and then we have a dictionary here that specifies what our nodes are. I happen to give them the name all nodes. And then I have this dictionary that specifies what my label is. So in this case, remember, every single node in my graph had a label of node as well as other things. So in this case, I'm specifying I want every single node in the graph. In practice, this is not a good idea to do. Just for the sake of demonstration, I'm doing it today. And I'm also going to put some properties into that in-memory graph, specifically my word vectors. Okay. My next dictionary here is my relationships. Okay, and I'm specifying all relationships, also not a great idea, but that's what we're going to do here. Orientation, you guys know that graphs can be directed or undirected. GDS, a lot of GDS algorithms prefer undirected graphs, not all of them, but a lot of them do. So I'm just going to call it undirected right now. All that's going to do is double up the directions of the relationships. Okay, and I'm going to put that in here, and we're going to create an in-memory graph. Okay. In just a second, we should get some information on that graph. You can say I have nodes and I have a whole bunch of relationships. Okay, so that's good. Now, we need to create our graph embeddings if we're going to do machine learning. And this is lines 91 through 93. GDS has node-to-vec built in. Okay, so I'm going to just copy and paste these lines in here. I apologize, this is going so fast. And then I have this thing called .stream. And what .stream does is it says, just write the results to the screen just so I can take a look at them. And I have this thing called embedding dimensions. So I'm going to give a 10-dimensional embedding. And in just a second, we'll see this to the screen. Okay, so I have lists of floats and they're, 10-dimensional. Cool. All right, one thing I didn't point out is this thing, GDS util as node. When you pull in your subgraph, your graph projection, it is not going to pull it in and anything that you would recognize. It creates these integers that don't correspond to anything physical. So we want to convert them back out into something physical. So I have my names and my embeddings that I'm pulling out here. But let's do let's actually write those to the nodes because that's how we're going to get them into Python. Okay, so I'm going to create a node property here, which is called n to v all nodes. Okay, let's give that a run. In just a second, all of those nodes get properties. Now we can go back into Colab and we're going to do some actual machine learning. So I'm just going to import a whole bunch of packages. Now, here's an important thing. We need to connect to our database. And how do we do that? Let's come back to the Sandbox UI for a minute. And I'm going to click this down arrow button. And from there, I click on Connection Details. Okay. Here you see I have this Bolt URL. And I'm going to copy that because that's where our sandbox lives. I'm going to paste it into this variable here called URI. My username is always Neo4j, and then I need a password. My password is always some 3-word thing separated by dashes. So I'm going to copy that in, and I'm going to paste it in. Give this a run. And if I get no errors, it means I am connected to my graph, which is cool. I have some entity disambiguation things here. I don't want to run those right now for the interest of time, but basically it's just looking at how many nodes overlap between two things, because maybe you could say that if they have a lot of nodes in common, that there's a high probability of there being the same node. Okay, here's where we're actually going to get to it. Okay, so I'm going to like I said, you can do Cypher commands from within Python. And in this case, I'm using the PyToneo driver, the community driver. And you see, I'm just going to return all of my nodes. I'm going to get their name, their labels, and then these PPTU things. And I'm going to write it out to a data frame. That's all this is saying. Okay, so let's do that. Okay, cool. So what we see here is I've got I've got my names, I've got labels. I've got these columns though, PPTU, person, place, thing, unknown. We're going to use our vectors to actually try and do a multi-label classification problem, a multi-class classification problem, sorry. And we're going to compare the outputs of our word vectors to our node vectors on were we able to do this classification. Okay, I just have some helper functions here to get everything into a format that scikit-learn likes. We're going to use scikit-learn here. So just don't worry about that. Here's our actual model. Okay, we're going to do a 5-fold validation using just really basic support vector classifier. We do a train test split. Okay, and then all we're going to do is we're just going to measure an accuracy score. We're going to return the mean accuracy scores. We're going to plot a confusion matrix. That's all we're going to do, kind of standard stuff. Okay, so let's do that for our word vectors. So we're going to see how well we predict people based on our word vectors. So running that, first off, what I want to show you before I get too excited here is I have a big class imbalance problem. And when you think about it, here's my accuracy. I'm getting roughly 84% accuracy, which is really not that bad. 50% accuracy means I'm doing as well as a chimp flipping a coin. Okay, but that's not that bad. You can see though that there are things that I do better on. 0 is, what is 0? 0 is a non-person and 1 is a person. So I do better at getting accurate on my non-people than my people, not surprising due to the class imbalance. Okay, but let's do that same thing now using my node vectors. Okay, so now we're going to use our graph vectors here to do the same thing. Okay, and here we go. I have 82% accuracy. Now let's stop and think about what that means for a second. I have roughly the same accuracy as I did for my word vectors, but my word vectors, if you recall, were 300-dimensional, and my node vectors were only 10-dimensional. Further, Spacey, which generated those word vectors, has all kinds of optimizations built into it. I didn't do anything to optimize these vectors at all. There's all kinds of hyperparameters you can tune here. I didn't do any of them. Okay, so if you think about that, that's actually pretty impressive. I've now compressed my embeddings from 300 dimensions down to 10. Okay, very, very cool. Now, I'm not going to run through these. You can see that we could do places, people, things, etc. So again, tuning the hyperparameters is important. Also, I used an incredibly basic, no hyperparameter tune support vector classifier. Okay, there's nothing about that that's tuned. This kernel thing just says, yeah, my classes are going to be imbalanced, do your best. Okay, so there's nothing that I tuned in the model. That's just like straight out of the box. That's kind of cool if you think about it. Okay, cool. Let's now, I'm going to just stop sharing really quick to see if there are any questions. How do you determine the value size for the embedding? I saw you had 10, totally arbitrarily chosen. If you go into my Medium posts, my most recent Medium post shows an actual tuning of the hyperparameters of one of the other embedding algorithms called FastRP, which you're going to see in the next example. So yeah, just look at that. I think Google uses an ontological concept called thing, everything. Okay, good to know. Thank you for that, Aftab. I hope I'm not mispronouncing that. Okay, cool. So let's move on. We're going to move on now to method 2, which was our Wikidata method. I'm just going to quickly scroll through the notebooks that show this. So Wikidata KG, so that's notebook number 3, assuming I can pull it up here and GitHub doesn't give me issues. Okay, so it's going to start out the same way. We're going to be creating our text and our named entities using the same thing that we did before. In this notebook, we're actually going to be using the official driver, the Neo4j driver, and I show you how to use that in a minute here. Okay, so this is just all the same stuff that we saw before, but I'm going to get an entity list that kind of looks something like this. I got a whole bunch of cleaning to do. You know, yes.
I think you have posted the slide share, the screen share.
I've posted the slides. I do have some.
You have paused the share, the slides, the screen share.
I've paused it and I haven't resumed it. Okay. Unpause sharing. Okay. Is this better? Are you able to see my screen now? Okay, yes. Cool. Yes. Thank you for the reminder. Okay, so just if you're looking at notebook number 3, just know that we're doing all pretty much the same stuff that we did in 2. We don't have to get the verbs though. So that's going to make it a little easier. And here's the list of named entities that we're going to get. Okay, I mentioned before we use a bot, PyWikibot, to interface with Wikidata. Okay, and this is how we do that. No biggie. This is just walking you through how all of that happens. You can scroll through this on your own time. There's a whole bunch of comments here. We don't actually get Wikidata entries for everything. For example, let's look at this one, Republican nominee John McCain. So Spacey said these were all grouped together, but really probably the thing that we wanted was John McCain. There's other things in here that don't have entries within Wikidata, and that's fine. We're still going to get a reasonable graph. Okay, so I can see that I'm getting my named entities, such as Barack Hussein Obama II, and Q values. So those are the Q codes that are in Wikidata. Now, how do we get the verbs? This is, remember I said before that you actually have to specify your verbs, which was the downfall of this approach. So what I did was I just kind of went through and I grabbed a whole bunch of P codes that I thought might be useful. Okay, so I have I just personally curated a whole bunch of these. So what this is doing is it's saying for every subject or object, every Q code I have, go and see if these P codes exist there. And if they do, then we're going to add them to the graph. Okay, this actually takes a little time. Another reason we're not doing this, this one took, not quite 10 minutes. But ultimately, the goal is we get this data frame out. In the pandas data frame, I have a source name, Barack Obama. I have Barack Obama's Q value. Here's my relationship. I have my relationship name, and then I have the target. So I can say Barack Obama's place of birth was this particular hospital, which has a Q value of that. Okay, now if you actually go through all of the code in the previous example, one of the questions that I ask is where was Barack Obama born? And there's a few different ways that you can solve it. I just want to show you because what you're going to see here is kind of fun. So we're going to go into cipher queries. Okay, back into our method 1 queries. Scroll down a touch. Wait a second, where did it go? Where was Barack Hussein Obama born? Okay, there are ways of solving this one that are, you can solve this a few different ways. Let me show you two. The first one, okay, so I'm going to match a node, and I have a property name of Obama. This is just another way I could have specified where n.name equals this. I'm just showing you a different way to do it. Connected to some other node. Okay, this is the ASCII art I was talking about. See how I have this arrow that's like one node, round parentheses, connecting to another one, round parentheses. Cool. And then I'm square parentheses, square brackets means relationship. So I could specify the type of relationship that they're connected through. Before I tell you what this asterisk stuff means, I'm just saying that P here has to be either of label country or label administrative area or continent or place. Okay, now here's a fun thing right here. When I do asterisk 1.5, what I'm saying is any type of relationship between 1 and 5 hops between N and P. That's like playing 6 degrees of Kevin Bacon here. So how many hops, how many actors do I have to go through before I land at Kevin Bacon? Stop and think about this for a second if you're a SQL person. Okay, if you do this in SQL, think about how many joins you have to do to make that work. People always ask me, how do I know if I have a graph problem? Big hint. If you have more than a couple joins in SQL, you probably have a graph problem. Now, why would I care? Well, first off, this is a super simple query to write, right? This is like one line of, match me this, select me that. Okay, super simple. It's also way faster. We all know that joins are expensive. They take time. This doesn't take much time at all. Watch this. So 1 to 5 hops. Let's look at it as a graph. And I got a whole bunch of answers here. Okay, I see that 1 to 5 hops took me to Mexico, the Pacific Ocean, Iran, the Caspian Sea. Obviously, these are not good answers. Some of them are Honolulu. But let's actually look at Honolulu for a second. Okay, I don't know if you can see it, but the name, move. The name of the relationship type here is bear. Okay, bear is the lemma of born. So I could probably make this a little bit better if I used the proper lemma. Okay, so here I'm going to say the same thing, but now I'm going to say either bee or bear. Okay, so if I do that, what do I get? Now that I've specified my relationship type, I have a much smaller graph. I see that Obama, bear, Honolulu. Yes, born in Honolulu. Obama B, United States, Obama B, I could probably just get rid of that B thing and I'd have the right answer. So that's cool. Okay, now, remember I was talking though before about how we did this. Let me get back to my notebook. How we can do this with Wikidata. And back in notebook number 3, bouncing around a lot, but it's all in the GitHub repository. So if I go down to those P codes, okay, here I specified P19, which stands for place of birth. So you can kind of get a feel for, where we're going here, that this could be much more accurate. Now, here's something else I need to do. I already have a blank sandbox instance running. I don't, you can only run one type of sandbox at the same time, okay? But I'm going to want another one because I just kind of want to keep this graph around for a while. Okay, and I'm going to scroll down here. And what I will find, there's this thing called blank sandbox graph data science. Okay, so that's another one of the blank sandboxes here. Sometimes this will appear here, sometimes it won't. There is a link in the repository if you don't see this box here. Okay, but I'm going to just click on it. I'm going to click create. So I'm creating a blank graph data science sandbox instance now. These take a little longer to create. They've got a little bit more memory and they have a little bit longer timeouts on them. So I can tell you right now, if I click that open button, it's probably not ready yet. But we will be populating this graph just like we did before. So I'm going to go back to Cipher queries now. Okay, and I'm going to go into the starting queries because I have a line here that's going to go grab a JSON file with the pre-populated graph. Okay, but let's close that browser just so we don't get confused. going to try opening this and see if it's ready. Okay, good. So I have my little green scroller bar. Remember, if I didn't have that, or if I got some sort of 404 bad gateway, you just want to wait a second and refresh. Okay, so we'll give this just a second. Yeah, this one usually takes a little while longer. Okay, cool. We got it here. One thing you might notice is that it might ask you for a username and password when you get in here. Sometimes it stores it in the cookies, sometimes it doesn't. Username is always Neo4j. And then the password, I'm going to just remind you how we got that. We click this down arrow button and I click connection details. Here's my password. Here's my IP address. Good to go. All right, so let's populate this graph. I'm going to copy line 25 into my browser. And again, if you get a timeout here, don't worry. The thing that we care about is, did we get stuff into my graph? And it's going to be 13 or 1400 nodes-ish. I can't remember for sure. Okay, good. 1325 nodes. Okay, 1600 relationships. Nice. Okay. I'm going to just look at it really quick, make sure it makes sense. I'm going to match node, return node. Okay. And I have a graph. Yay. Okay. And interestingly enough, here's Barack Obama, our search term, but he's not actually in the center of the graph. The United States is. That's kind of interesting. Neat. Okay. Let me close that just so we're not burning through memory here. Okay, what are we going to do with this graph? We're going to go into method 2 queries now. Okay, method 2. We have duplicates. There are not many of them just by virtue of us using Wikidata. So I'm going to copy lines 10 through 13 of method 2 queries in here. Just get rid of them. It's the same process as before. I only had 6 nodes, so that's cool. Now, you remember before we had that list of node types. We had like, this was the Taylor Swift was a thing and a person. We have those here too. They're in a slightly different format. And so I just have lines 16 and 17 to deal with them. And then there's a second query. My second query, update the node labels, is lines 20 through 22. Okay, it's just dealing with the fact that Cypher and Neo4j prefer lists of strings and they have to be formatted a certain way. So if you really want to get into the weeds on that, you can go look at the JSON files and see how it's different. But now I have a graph and it has different labels to it. So I can see sovereign states are red, which would be like the United States, humans, blue, and I can look at some of these entities and they actually do make sense. So like Barack Obama, Sonia Sotomayor, Elena Kagan, Merrick Garland, Mitch McConnell, Joe. Okay, so these are all clearly people. I have private universities are in blue. So here's University of Chicago. If you don't see it at the very, I'm hovering my mouse over that university node, and at the very bottom it says name University of Chicago. Okay, so that's good. We've got a graph. What do we do with it? Well, let's do the where was Barack Obama born case. These are in a file called answer queries, which I will upload to the repository hopefully later today, maybe tomorrow. Okay, so now I'm getting very specific. The more specific you can be in a Cypher query, the better, the faster it will run. So I have a node with the name Barack Obama is going through a directed relationship called place of birth to another node. Okay, now if I wanted to get really specific, I could say that my node label was person or human or whatever it is. I don't exactly know what place I'm going to get back here, so that's why I'm just going to say all nodes. Okay, and I have 3 of them. So I have the hospital that he was born at, and I also have that he was born in Honolulu, but interestingly enough, we also have Kenya here. And if you follow US politics and news, there was this whole thing going on when he was president of, oh, he wasn't actually born in the United States, he was born in Kenya. Okay, that's reflected in Wikidata. It's just part of the data. And again, subject matter expert involvement. A subject matter expert can come in here and say, no, that one we want to throw out. Okay, so cool. Now we're going to do the same problem. We're just going to do place versus non-place. Okay, and it's just a binary classification problem this time. Okay, so I'm going to get all my nodes, and I want my node type somewhere in this list. Now, this is a hand-curated list, I admit it, but I've got a whole bunch of things that a whole bunch of labels that I discovered out. I didn't even know what some of these were, but I discovered that they're all places. And for those, I'm going to set a property on my node called isPlace equals 1, very similar to what we did before. So we're going to copy lines 27 through 62. Okay, we'll just throw that right into browser. There it goes. Okay, so we've set a whole bunch of properties for things that are places. Now, we also need to set our non-places. Okay, this is a much easier one. So if isPlace is null, then we're going to set that value equal to 0. Okay, so let's go back and do that. Okay, danger. We have 413 places and 906 non-places. So we've got, again, a class imbalance problem. It is what it is. We just got to deal with it. This is life. Okay, so now we're going to do some machine learning, of course, to do our binary classification. It's going to be just like before. And we start off, as we do with all things in GDS library, by creating an in-memory graph. Again, I'm using every single node, not a great idea. I'm using every single relationship, also not a great idea. This is just for demonstration purposes. Okay, so I am going to copy and paste that into browser. One of the things I will tell you is that creating these in-memory graphs can get very sophisticated. And I'm going to show you a link at the end. It's also linked in the repo. I do an online video series called Bite-Sized Neo4j for Data Scientists. And the goal is to provide every week one 5-minute video showing how to do one concept within Neo4j. And I have a few videos on how to create these graphs. So, don't worry if this syntax isn't quite making sense. Okay, now before I do my machine learning, I need to create my embeddings. So just like before, I'm going to use node2vec and create a 10-dimensional embedding. So I'm copying lines 86 through 91 into browser. Okay. And then the other thing I'm going to do, just for fun, there's 3 different methods for, I'll say 3.5, for creating node embeddings within Neo4j GDS. That was node2vec. This one here is called FastRP. It's, as you might get from the name, it's fast. But again, I'm creating just a 10-dimensional vector. It does a slightly different skipgram to what node2vec does, but it's still just randomly hopping around the graph. Okay, I've done nothing with hyperparameters other than saying I want 10 dimensions for my embeddings. All right, so now I have embeddings created, and now we can do machine learning. Okay, so I'm going to go back into my starter collab thing, and I'm going to open notebook number 4. I'm going to open that in its own tab. Okay, and like I said, we're using this time the official Neo4j Python driver. We need to install it. Okay. So we'll give that a second. Okay, there we go. We're going to install, or we're going to import a whole bunch of packages just like we did before. And then I have this class here. This is just like this nice class for making a connection to our database, just kind of a nice Pythonic way for handling the connection as well as the queries. So let's just give that a run. Now we need to connect to our database. I'm going to remind you how to do that. We come back here to our Sandbox UI, and I'm going to click on my IP address here, my Bolt URL. Put that in here, and then I'm going to click on my password. Oops, here's my password. One of the things I always do is grab the other Sandbox's password or URL. Okay, so now I'm going to run that. Slightly different syntax. It probably looks really similar to like SQL Alchemy, how you would like query a database there, where I have like a connection and I have a query. I like this just because I return the number of nodes. Okay, so match n, return count of n tells me I have 1,319 nodes. which is good. So I know that I've made the connection and that I see the full graph. Okay, so let's just quickly, remember I was showing TSNE plots before. I'm going to just quickly do that. I have a function here for doing that, just so we can see, what's kind of the quality of our embeddings. I'm just going to do it for one of them. I'll do it for Node2Vec, just because this can take a minute to run. Remember, we want to see our red nodes all clustered nice and dense together, and our blue nodes all clustered nice and dense together. And sadly, that's not what we see. We see that there are some clusters that look all right, like this one, that's this blue cluster at roughly 3 o'clock, but it's kind of a mess. It is what it is. But when we see something like that, we might expect that we're not going to get super great results. But let's see what happens. Going to go down here. Again, I'm just creating my data in the format that scikit-learn wants. And then I have my same old model before, 5-fold validation, support vector classifier. Here's my, this is my attempt to balance the class weight. I misspoke on the previous one. Or balance the classes themselves, because we know there's a class imbalance problem here. Okay, so I just have these functions. And again, we're just going to look at accuracy, just real super simple stuff. I'm going to create a data frame now. The way that you create a data frame using the official driver is a little different, but this is just the syntax for it. So I just give that to you here. Okay, so now I have my category. Again, this is just a binary classification problem. I've got my 10-dimensional vectors via Node2Vec and via FastRFP. So let's see what we get when we run this. Okay, I have roughly a 74% accuracy, not quite as good as before, okay? But one of the things I want to show you is that my confusion matrix looks a little better. I don't have, I'm getting roughly the same accuracies for my, my true and predicted labels, which is good. That's better. Let's do this for FastRP just really quick. It's not great. It's nothing to write home about, roughly 70%. Again, consider though that I have 2 times as many negatives as positives in this problem. So that's actually really not that bad if you think about it. And also, again, think about this is only a 10-dimensional vector. These are not optimized for anything, okay? Well, you could go through and predict unknowns here, but y'all know how to do that. We're not going to do that right now. So, play with this stuff. You can go read my blog posts on how to tune these embeddings. I will tell you, one of the interesting things that I saw, I recently gave a talk at the Open Data Science Conference, like last week, 2 weeks ago. And what I did was I showed that doing a classification problem, just it was a multi-class problem, and it was only 2,000 data points, and I was doing word embeddings versus graph embeddings. My word embeddings were getting me like 73% accuracy. My graph embeddings, though, were getting me 87% accuracy. So sometimes it really matters if you can take into account those graph embeddings. They really can help you. Unpause sharing. Let's go back to our main slides now. We're going to be wrapping up from here. Okay, so where do we go from here? What can we do with this? Well, first off, let's just be reminded of our 2 key concepts. Again, these were the 2 things that if you took nothing else away from today, that I wanted you to remember. First, there is no proverbial quote-unquote silver bullet associated with natural language processing. It's hard, text is noisy, you need subject matter expert involvement, you need an NLP expert if you at all can get them. Second, the quality of what you get out depends on the quality of what you get in. So you saw places where our verbs were really bad, right, in the first method, or you saw places where I had to really very clearly specify my verbs. In my view, I got a better graph in doing that. The machine learning model didn't come up as good, but at least the accuracy didn't. But it certainly made for a much cleaner, easier to understand graph. Okay, where we go from here. First off, these are really small graphs that we were looking at. A few hundred to 1,000 nodes, that's nothing. When you start getting into some serious graphs, you're talking millions of nodes. You can be talking billions of relationships. So anytime you can add data to these graphs, it's going to help you. Then I also mentioned several times various embedding optimization techniques. I didn't optimize our embeddings at all, not at all. Each of these has a lot of knobs to turn. Node2Vec has a ton of knobs. FastRP has like 4 knobs that you can turn, and they really, really impact your overall results. So go check out my blog post on that with FastRP. Then adding data for creating vectors or creating those embeddings. Now you remember that we used Spacie to create word vectors of those descriptions that the Google Knowledge Graph had. Well, it turns out that you can actually use those for enhancing your graph embeddings. They can be used to help create those graph embeddings. I didn't do that today, but if you look at something like FastRP Extended, remember I said there was like 3.5 embedding techniques built into GDS. FastRP Extended is like normal FastRP, but it takes in other embeddings like those or other bits of data like the word vectors. So I leave that as, as an exercise to the attendee. And then these different embedding modeling techniques. There's a pretty sophisticated one called GraphSage, also built into GDS, also can take in node properties. But I want to call out graph neural networks because everybody always says, well, can I use TensorFlow or PyTorch or whatever? Absolutely you can. And in fact, we just have a list of floats. If you can convert that into a tensor, you can throw it into any neural net that you want, but it turns out that there's actually neural networks, like you have convolutional neural networks, you also have graph neural networks, which are specifically tuned to it. There's all kinds of different math that's involved there, but it's absolutely, absolutely doable. Okay. So what problems could we solve once we have this? Well, first of all, community and cluster detection. That's obvious with any graph, you can do that. Node classification, I demonstrated some of that today. When I did the place versus non-place or person, place, or thing. But link prediction. So link prediction, those of us in this conference know it's like, hey, what's the probability that Michelle Obama, who might not be connected anywhere else in this graph, but what's the probability that she's connected to Barack Obama? Just looking at the graph itself. Graph-to-graph classification, super huge, super beyond this course subject. Unstructured text and natural language processing. Remember, I showed how words are connected to other words, just like nodes are connected to other nodes. So you could create your whole NLP thing just in graphs. And then, question answering systems, recommendation engines, things like that. Anything that you can do with normal, traditional ML, you can do with graph ML. All right, so with that, I just want to say thank you. Thank you for attending today. I love talking about this subject. I love blogging about this subject. You can find me on Medium there where all my blogs are. And then below that is my Twitter address. I unfortunately can't hang around too long today to take questions. If you have questions, please, if they're things that fit within the character limit of Twitter, please hit me up there. Otherwise, you can always go post. I'm on GitHub a fair bit. You can go post an issue within the repo, and I'm happy to answer any questions there. So with that, I am going to stop sharing. And I'm going to take a look and see what other questions we have here. What was the rationale behind manually annotating certain words, phrases as is places? The rationale was just for demonstration purposes. You could, so I was just trying to create a labeled supervised machine learning problem. In general, though, you're not going to have that, or if you're real lucky, you have that. So in general, what you're going to need to do is you're going to need to consider your unsupervised methods, such as, like k-nearest neighbors or some sort of, clustering algorithm using those embeddings. So it was just for cheesy fun. So if there are any other questions, Python returns a data frame from GraphRun. It can if you use the method .toDataFrame. It's one of the reasons I like Python is that it's really good at returning some nice Pythonic data structures. So, all right. Well, I see a lot of thank yous in the channel. And again, thank you all. Please come find me on the internet and enjoy the conference. It's always a great conference.